I'll get my screen share set up for 4.3. And again, it's done it for several times. I open both PowerPoints, but only one shows up. Okay, so when it comes time to go to 4.4, I'm going to have to monkey around and get it. Now everybody's back again, but Keelan, you're in the way. Let me scoot you just a bit to the right, I'm sorry. And I've got this taskbar that's also in the way. And let me scoot it down and over. Okay. Sorry about my throat. This past weekend did a lot of outside yard work, mowing and other things, and I just got completely congested. So if I sound a little hoarse, I feel a little hoarse. Okay, we're in Chapter 4, Trigonometry, Section 4.3, Right Triangle Trig, top of page 279, Example 3. So I've got to find that here. And this PowerPoint is awfully slow. Okay, there's example 1. Okay, I don't think we've gotten to trig identities yet. It's right before that. Okay, this I think was the last slide we did. Let me see if I can find that slide though. No, we aren't quite at that slide yet. Or at this one. Let's try this one. Okay, yeah. They skipped example 2 and 3 on the slide set, so we're going to pick up here and go. All right, let's go from current slide then. Sorry this is taking so long to get things manipulated. All right, now let's ask again. Any questions on anything we've done so far? Now this can be general questions outside the class or specific questions to trig. Any questions whatsoever? Okay, I hear no response, so I assume that means there are no issues. If that's the case, okay, here may be someone coming in. Yeah, Jalen's here. So let me let Jalen in. I should have taken a vote on that. No, I'm just kidding. Jalen is here now. Good deal. All right. Has anyone else seen anyone trying to get in? If so, I'll try to go back and find them. All right, Jalen, as I was saying, we're in Chapter 4, Trigonometry, Section 4.3, Right Triangle Trigonometry, and we're on page 279, top of the page, Example 3, which is not given on the PowerPoint slides. So I've got to get my book in lap here so I can read it. Get my Wacom tablet so I can write it. And let's go to the whiteboard. All right, now I've got more manipulation to do. Got to get this taskbar as much out of the way as I can. And let's move the whiteboard as far to the left and up as I can get it to go. Okay, that's good. So, probably for you it just seems like one big white screen, but for me I have to maximize it. So, we had just done, bottom of page 278, the 45, 45, 90 right triangle. That's sort of redundant because 90 means right triangle. Now we're going to do another really famous or popular one, and this is your 30, 60, 90 right triangle. Okay? Now, I think to start this, I'm going to try to draw the picture. And as you know, I don't draw too well. Okay? And I hear snickering in the background. Okay, so I'm going to draw a vertical line, or as close to vertical as I can. That seems to be okay. Not very vertical, but it'll do in a pinch. And then I'll do a horizontal line as closely as I can approximate that. Okay. Whoa, that's not very good. And then I'll do a connecting line here. Now y'all just have to imagine that this is a 30, 60, 90. It's probably nowhere close. Okay. Now, what the attempt here is to have each one of these angles be 60 degrees. If I can find my, oh, wait. I don't think anyone else is coming in, but let me check. No. Okay. Now, goodness, the pen is there, and then it flies off into Never Never Land. There it is. Okay. Now, obviously, this isn't quite a 30, 60, 90. Okay. Supposedly, this is 60 degrees here. Okay. You could call it pi thirds if you wanted to. The book is calling it 60 degrees, and it won't let me draw. Okay. This is so aggravating. I try to draw a degree symbol, and if that's 60, then this is 60. It doesn't look like it is, but let's just imagine it is. Well, then the bigger angle up here is also 60 degrees because the sum of the three angles of any triangle is sum of the three angles of any triangle, 180. So if two of these are 60, the third one's got to be 60. Now, if this line right here happens to bisect that angle, that means each one of these is a 30-degree angle, right? That would be 30, and this would be 30. This doesn't write threes very well at all. Okay. Now, so what we have on one side or the other is a 30, 60, supposing this is a right triangle here and here, that right angle here, that's what we call a 30, 60, 90 triangle. Now, here are things to note. What if we just arbitrarily somewhat define this side right here to be 1? That's from this point here to this point here. This would be a distance of 1. Well, obviously, this would also, if I did it right, maybe it's not obvious, but if I did it right, this would also be a 1. And since these are equal angles, they're also equal sides. And since this side down here is actually a 2, this would be a 2, and that would be a 2. Agreed? Because if they're equal angles, the opposite sides are equal as well. Now, from this right here, and we know this little triangle here is a right triangle, meaning that 1 squared plus whatever this squared is has to equal 2 squared. So let's just call this y, because it's going upward anyway. So let's say that 1 squared plus y squared is equal to 2 squared. Good old Pythagorean theorem, right? Let's solve for y. Well, this is 1 plus y squared is equal to 4. Let's subtract 1 from both sides, and you get y squared, because this adds 0. Y squared is equal to 3. Now, I don't care what y squared is. I want to know what y is. How do we undo a square? Anybody? Anyone? Take a square root. Okay? That undoes a square. So this y here is equal to the square root of 3. This doesn't do equal signs well either. It just refuses to write a 3 properly. There we got it. Okay. That's why, and the equal sign has an extra bar in it. I don't know why it does that, but it does. So the y is square root of 3. Guess what, team? It says use that equilateral triangle shown in this figure here. My figure is not quite as pretty as theirs. To find the values of sine of 60 degrees. Okay, well here's a good old 60 degree. What by definition is the sine? Remember that from last time? Some old hen? What was that? Perfect. And what is your opposite side from this 60? That 60 degree angle, what's its opposite side of that right triangle? The y value, which is? Square root of 3. So this will be the square root of 3 over its hypotenuse. What's the hypotenuse for that angle? 2. There we have it. The sine of 60 degrees is square root of 3 over 2. You could have written that as sine of pi thirds. That's the same thing, but just in radian. Sine of pi thirds is 60 degrees. We already knew that. We knew it from the unit circle. Here we've got it from right triangle trig. They also asked for a cosine of 60 degrees. And what would that be? Cosine is caught another hen. A stands for adjacent side. What's the adjacent side to 60 degrees? 1 over its hypotenuse, 2. So that's 1 over 2, or 1/2. You could have written this as pi thirds again. You didn't have to use 60. Okay. They also asked for sine of, well, let's just go on and complete the thing here and do the tangent of 60 degrees. Why not? Tangent is taking oats away. And the opposite was? Square root of 3. And the adjacent was? 1. So it's just square root of 3. And since we're there, let's go on and do the cotangent of 60 degrees. And you could call that pi thirds again. Perfectly fine. And that would be reciprocal of tangent, which is 1 over root 3. Which you could write as what? If you don't like having a radical in the denominator, root 3 over 3. Multiply numerator and denominator by root 3. That gives you root 3 over 3. What would be the secant of 60 degrees? That's reciprocal. Oh, is somebody else coming in? Hold on a moment. Yeah, here it is. Sharika's here. So let me pause just a moment here and get Sharika marked present. Alright, bottom part of the alphabet's coming through strong now. In fact, whole class is coming through strong. We're missing Damien and Kelsey and Jared. That's all we're missing of our regular attendees. Now, I don't know if anyone knows Jeremiah Bodie or Tiana Johnson. They were both listed as being in the class, but one of them did actually turn in something that first week on the, whatever they call it, syllabus agreement. The other one did not, and yet they're both still on the roll. Now, I really dislike the school policy now that if you do anything, you get counted as present. whether you've actually been to the class or not. And they're doing that, so one of those students probably is going to have to withdraw from the class because that student did turn in something, okay? The other student never turned in anything. That student should be dropped from the roll. As far as I know, they're still showing up. So beware of that. If you're not certain you're going to be in a class, be sure you don't turn anything in. Now, if those students haven't paid for it, then it's a nebulous point anyway. They aren't going to be kept in the class because they haven't paid. But that's another issue, okay? Hopefully they will not. If they haven't been here, hopefully they haven't paid. I can't guarantee that. Okay, sorry, that's my gripe of the week last week that they were doing that, though I've griped about it before. All right, so we did, we're on secant of 60 degrees, okay? By the way, now I can't remember who was the last one. Yes, it was Sharika. I don't know, Sharika, what was going on there. I don't know if you can hear me yet. I saw that you had were trying to join the class at something like 7 o'clock this morning, and I went, hey, it doesn't start till 10. I've got another class before then, because Zoom was telling me I needed to start the class. I thought, no, I can't start the class. I've got another class first. But anyway, glad to see that you're here now. But by the way, if you any that just came in, we're in Chapter 4, Trigonometry, Section 4.3, Right Triangle Trigonometry, top of page 279, Example 3. Now we're doing a little bit more than Example 3 is calling for, in that we're doing all 6 trig functions. They just asked for sine and cosine of 60 degrees. We're doing all 6. So what would the secant be? If cosine is 1/2, secant is the reciprocal of that. So it would be 2. Perfect. And what would the cosecant of 60 degrees be?
2 squared 3.
Okay, I think you almost said it right. 2 over root 3, right? It's the reciprocal of sine, but that is also 2 root 3 over 3. If you don't like having radicals in the denominator. Okay. Now, I think I pointed this out to you before, but let me say it again. Secant and cosecant always are going to be greater than 1 or less than -1. We're in the first quadrant, so they're always greater than 1. Sine and cosine are always going to be between -1 and 1. And since we're in the first quadrant, they're between 0 and 1. Tangent and cotangent can be anywhere, any value from -infinity to +infinity. Since we're in the first quadrant, anywhere from 0 to +infinity. But secant and cosecant can't be less than +1 if they're positive, and can't be greater than -1 if they're negative. So they've got to be outside of the 1-to-1. Sine and cosine in between -1 to 1, and tangent and cotangent can be anywhere. Okay, so we've got those done. They also ask, what is the value of sine of 30 degrees? So since we're here, let's do that. Sine of, and why it puts these extra streaks in there, I don't know. Sine of 30 degrees. Well, again, sine is some old hen. Now for the 30-degree angle, that's this one up here. What's its opposite side? Anybody? 30-degree angle up here, that's the 1. And what's its hypotenuse? 2. So it's 1/2. Now this also, by the way, is pi/6. 30 degrees is pi/6. Just so you get used to it. Let's do cosine of 30 degrees. That's called another hen. And what's the adjacent side for this 30-degree angle? Anybody? This square root of 3. And what's its hypotenuse again? 2. Square root of 3 over 2. That's an ugly looking 3, but it just doesn't draw threes well. That's why we're here. Go on and do the tangent of 30 degrees. And you can think of it as taking oats away, or just the ratio of these two. And that would be 1 over root 3, which, if you don't like having radicals in the denominator, square root of 3 over 3. While we're here, let's go on and do cotangent of 30 degrees, or pi 6 if you prefer radians, and that would be what? Reciprocal of tangent, and that would be root 3 over 1, or just root 3. Okay? Secant of 30 degrees, or pi 6, is reciprocal of cosine, which would be 2 over root 3, or, if you don't like radicals in the denominator, 2 root 3 over 3. Okay? And finally, the cosecant of 30 degrees would be what? Reciprocal of sine, which would be 2. Got it. Okay? Now again, this is re-emphasizing something we talked about before. Notice here, the sine of 60 is the same as the cosine of 30. Okay? Why? Because 30 and 60 are complementary angles, so this is the complementary sine for that one. They are the same. The complementary sine of the complement of an angle is going to be the same as the sine of that angle. Similarly, cosine of 60 is the same as the sine of 30, 1/2. And tangent of 60 is the same as the cotangent, complementary function, so that's the same as cotangent of 30 of the complementary angle. Tangent of 30 is the same as cotangent of 60. The complementary function of the complementary angle are the same. And same with secant and cosecant. The cosecant of 60 is the same as the secant of 30, and the cosecant of 30 is the same as the cosecant of 60. So you see all those things playing out. Now, frankly, 30, 60, 90 was much easier to do with right triangle trig than it was with the unit circle. It was doable with the unit circle, but it was a little messier. So straightforward here in this one. So that was example 3, top of page 279. Any questions on it? Okay. Now, as always, after every example, there's a checkpoint, and the checkpoints answers are in the back of the book, just like the answers to the homework problems are, but also they're located at Audio Video Solutions in English and in Spanish at larsonprecalculus.com, whereas the problems in the each section are at calcchat.com, but the checkpoints at larsonprecalculus.com. So let's go back to our, goodness, I don't know what was flashing there. I think it's this one. Nope, it's this one. Yeah. All right. All right, we've got to go back to the original current slide, and we'll proceed from here. This is example 1 we did a long time ago. All right, here we go. this is a table. They say example 1. It's not just example 1. All of the examples we've done, you're given lengths of two sides of a right triangle but not an angle theta in some of these. Often you'll be asked to find the trigonometric functions of a given acute angle theta. To do this, construct a right triangle having theta of one of its sides as one of its angles, and then go. Now, that verbiage at the top really has nothing to do with, or not much to do with, the table at the bottom. This is just saying what we just said, that the sine of 30 is the same as the cosine of 60. Okay? The complementary function, cofunction for cosine for sine, complementary function of sine would be cosine, of the complementary angle, this is sine of 30, that's the cosine of 60, the complementary angle for that, those have the same values. And sine of 45, cosine of 45, of course they have the same values because you're on that one-to-one line. Sine of 60, same as cosine of 30. Complementary function of the complementary angle are the same. And they don't show tangent and cotangent, but they would be too. The tangent of 30 would be the same as the cotangent of 60, and the tangent of 60 the same as the cotangent of 30. And tangent of 45 is the same as cotangent of 45. They're both 1. Then the two that you don't see anything on are secants and cosecants. Same deal, because they are reciprocals of sines and cosines. So if it's true for sines and cosines, it's true for secants and cosecants. All right, that's that table that we, I think, talked about. In fact, that we did. I showed the table and then said, sorry, we should have the paragraph up here, okay, right here, was on page 278. The table down here was on 279. That's why I said this paragraph really doesn't have that much to do with that table. Okay, but now that we're through with that, let's move to the next one. In that box, see, this should have been at the bottom of that thing. Note that the sine of 30, 1/2 is the same as cosine of 60. We've said it a dozen times now. This occurs because 30 and 60 are complementary angles, and sine and cosine are complementary functions. Sine function and complementary of the sine, cosine. In general, it can be shown from right triangle definitions that cofunctions of complementary angles are equal, which I said time and time again. And here's Courtney. I think he was already here. He must have either had to go or got bumped out and has come back. Yep, already have him here. Good deal. Welcome back, Courtney. Okay. So these relationships are true. The sine, and we may have done this one before, the sine of the complement of theta is the cosine of theta. The cosine of the complement of theta is the sine of theta. The tangent of the complement of theta is the cotangent of theta. The cotangent of the complement of theta is the tangent of theta. The secant of the complement of theta is the cosecant of theta, and the cosecant of the complement of theta is the secant. Okay, so the cofunction of the complementary function of a complementary angle is the same as the function of that angle. Okay. Any questions on that? All right, I think the next slide, if I can get it to advance, sometimes it makes me click on the slide. Okay, before we get there, example 4, okay, using a calculator. So let's go back to the whiteboard. Does anyone need me to leave this up a little bit longer? Anyone? Okay, I'll delete it. And it says now, and this is why they throw this in now, I'm not sure, but it's perfectly fine. I guess I had to put it somewhere. Use a calculator to evaluate the secant of 5 degrees, 40 minutes, and 12 seconds. Now don't try to make your calculator do all the work. It's just a box, okay? It can't do it all. You've got to do some of the work here. Let's first figure out how many degrees we're talking about, okay? So what that means is we need to convert this number of seconds into either minutes or into degrees. Which way do you want to go? Now, I'll tell you how I like to do it. Let's take the 12 seconds first. Okay? Now, I'm going to multiply that by a conversion factor. It's a pretty simple conversion factor, and you may not have to do this. You may know it already on your own, but I want to get that to minutes. Now, double quote means seconds, single quote means minute. I always like to do my conversion here, 2 blanks, one for numbers, one for units. Always put the units in their place. Same as we did when we were doing degrees and radian conversion. Okay, so here we want to put seconds in the denominator, minutes in the numerator, so you can cancel them out. Then the question is, how many seconds are in a minute, or how many minutes in a second? We know that 1 minute is 60 seconds. That's true in time, is true in angles as well. So in other words, divide the 12 by 60, and by the way, that would be a 5 here and a 1 there, because 12 will go into 65 times. So this is 0.2 minutes. Let's add that to the 40 minutes. So that gives 40.2 minutes times blank blank equal blank degrees. And this time I'm going from minutes to degrees. So therefore I want minutes down here, degrees up here. 1 degree is again 60 minutes. Think of a degree like an hour. Okay. So this isn't going to be quite as nice, but let's do what we can. 2 will go into this 30 times. 2 will go into this 20.1 times. Now I can't do any more with my just doing it in my head, so I'm going to pull out my handy dandy calculator, which happens to be my telephone. Okay, so I have to get into calculator mode here. Alright, now for the first part here, I can use it upright like this. All we're doing is dividing 20.1, or you could be dividing 40.2. It doesn't matter. Calculator can do both of them. Divide that by 30, or 60 if you're using the other one, and that gives me 6.67 of a degree. So that's what I'll write here. This is 0.67 degrees. 0.67 degrees. Now if you have a real fancy dancy calculator that you could put in that many minutes and seconds and it gives you the right answer, use your fancy dancy calculator. I'd have my telephone that won't do that. So really our problem now has become find the secant of 5.67 degrees. There's our problem. My telephone, and I bet you your fancy little calculator, even when you turn it sideways, will not have a secant key on it anywhere to be found there. So therefore what we do is say the secant of 5.67 degrees is the same as the reciprocal, or 1 over the cosine of 5.67 degrees. Now I'm going to show you sort of the easier way to do this rather than 1 divided, but that works quite well. But let's get your calculator, and it's got the 0.67, so I'm just going to add 5 to that. plus 5 equal 5.67. There we have it. Now I'm going to press the cosine key. Now mine is somewhere right there, I believe it is. So I'm going to, oh wait. Before you do that, notice here I'm in radian mode. I don't want to be in radian mode. I need to be in degree mode, so I'm going to come down here and press degree. Now the radian disappeared up top, and you can change back to radians down here, but when on this phone, if you don't see the radian, you're in degree mode. Okay, so now I'm going to take the cosine of that by pressing the cosine key, and that gives me a number awfully close to 1, but not equal to 1. And that's not surprising, because 5 degrees is just a little bit above 0. The cosine of 0 is 1, so you haven't gone far, but that's the cosine of it. To get the secant, all I press is this 1 over x key right here. That's the reciprocal key. So I'm just going to press that key, 1 over x, and that gives me, oops, I can't write on the screen there. That gives me 1.0049, blah, 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 blah. Okay. There's the secant. Remember I said secants and cosecants are always greater than 1 or less than minus 1. This is just barely greater than 1, and that's because you're just a little way from 0 degrees where secant is equal to 1, and now the secant's increasing ever so slightly. Let's see how the book did. Okay, they got 1.049166. I got 1.004916617601951. In other words, it's an irrational number, which you would expect. Don't expect it ever to be an n. I'd say 1.005 would have been a perfectly good answer. It's all approximate. That's good enough. All right. Any questions on how to use a calculator and the procedure you use first to get seconds to minutes and minutes to degrees? That's what we did over here. Seconds to minutes, minutes to degrees. And then to get the secant of so many degrees, find the cosine of that many degrees and then reciprocate. And that gives you that. Any questions on that? Always keep in mind, does the answer make sense? In other words, if it's a secant, it better be greater than 1 or less than a minus 1. Greater than or equal to 1 or less than a minus 1. Excuse me just a second. I've been talking since 8:30 this morning, so the throat's getting a little dry. All right. After example 4 we just did, there's also a checkpoint. Please do the checkpoint. All right. Let's go back to 4.3. Okay. And go back to current slide. And go to trigonometric identities. Folks, you're going to be seeing these till the cows come home. You will be using these, okay, till way after the cows come home, okay? You're going to do these over and over and over again, okay? So get to know them. These are important. We've seen them before. You saw them with the unit circle. Here they are again. In trigonometry, a great deal of time is spent studying relationship between trigonometric functions, and those relationships are often identities. We used them in 4.2. We're using them in 4.3. We'll use them over and over again. Entire chapter 5 just about is going to be dealing with using identities. Here are the fundamental ones. We've said them over and over again. Hopefully you've gotten to know them already. Sine is reciprocal of cosecant. Cosine is reciprocal of secant. Tangent is reciprocal of cotangent. Cotangent is reciprocal of tangent. Secant is reciprocal of cosine. And cosecant is reciprocal of sine. They just go. That's what makes trig so neat. Everything fits. You just have to remember where. These are often called the reciprocal identities. Seems like there is another name they sometimes use, but reciprocal identities, I think, says it best. These two special ones here, tangent is always sine over cosine. You remember I said that. And cotangent is cosine over sine, because cotangent is reciprocal of that. So these. Now these are called either quotient identities. Other books call them ratio identities. So if you ever hear me say that, that's because some of the books I've taught from call them that. Let me see if I can get it. The ratio identities. I'm going to abbreviate that. Quotient identities are ratio identities. Now, here are the ones. These are fairly easy to remember. We use them all the time. These we'll use all the time, but are a little bit more involved because they have squares in them and they have additions, not just divisions and multiplication. They have additions and squarings and all sorts of things. Here is your fundamental Pythagorean identity. Sine squared theta plus cosine squared theta is equal to 1. Please, please, folks, remember that one. Now let's do it from the viewpoint of our right triangles. Okay? Now I'm just going to try to draw a right triangle here. If I can get my pen to cooperate, here we go. Let's just say here is let's just pretend that's a right angle. And this is your angle theta that you're dealing with. Okay? This is the opposite side, the adjacent side, and the hypotenuse. Everybody agreed? What is sine? Sine is opposite over hypotenuse. What's sine squared? That would be opposite squared over hypotenuse squared. Plus, what is cosine? This is sine. Some old hen. What is cosine? Caught another hen. This is another hen. I put the C up there. Caught another hen. That's adjacent over hypotenuse. So the square of cosine would be adjacent squared over hypotenuse squared, right? This is for any angle whatsoever. This isn't one of our special angles. Any angle in a right triangle is going to have that relationship. Well, what is that? We have a least common denominator of h squared, and your numerator is o squared plus a squared. But this is why it's called Pythagorean identities. Where's my pen? Come on, show up somewhere here. There we are. Okay. O squared plus a squared, those are the two sides of a right triangle, is equal to h squared. So this is h squared over h squared, which is 1. That's why it's called the Pythagorean identity. Okay? Because it's always, always, always true. Because Pythagorean theorem is always true. Now, I don't know if you're interested in this, but I'm going to do it anyway. I'm going to take that first identity here, and I'm going to divide every term in it by cosine squared. Okay. Pretty ugly 2 there. Okay. Well, what's sine squared over cosine squared? From up here, sine over cosine is tangent, so sine squared over cosine squared would be tangent squared. There it is. What is cosine squared over cosine squared? That's the same thing over itself. That's 1. 1 plus tangent squared is equal to, what is 1 over cosine squared? 1 over cosine is secant, so that would be secant squared. So this one comes directly from this one. 1 plus tangent squared is secant squared. Do the same thing, but divide by sine squared. That would be a 1 there. Cosine divided by sine is cosecant, so cosecant squared. and 1 divided by sine would be cosecant, cotangent squared. 1 divided by sine would be cosecant, but squared, that would be squared. So these two come directly from that one. Okay, they all come from the same place. Now, I wish I could erase screen because I want to show you some other things. Here's a few others. What if we subtracted a cosine squared from both sides? That would give us sine squared is equal to 1 minus cosine squared. And guess what? We could take the square root of both sides and have sine is equal to the square root of 1 minus cosine squared. Of course, with that, you have to have a plus or minus in front. But if you're guaranteed to be in the first quadrant, you can leave it plus. Okay? And similar to that, we could have subtracted sine squared from both sides and had that cosine squared is equal to 1 minus sine squared. And by the way, you're going to use that a lot in these forms as well. And then you could take the square root of both sides and have cosine is equal to the square root of 1 minus sine squared. And if you could be anywhere, that would be a plus or minus. But if you know you're in the first quadrant, then it's the positive square root of 1 minus sine squared. Here you could do the same thing. You could subtract 1 from both sides, and that would give you tangent squared is equal to secant squared minus 1. And then you could take the square root of both sides again. Or you could have, now this is a little bizarre, but you could have subtracted tangent squared from both sides, and you would have secant squared theta minus tangent squared theta is equal to 1. Because if you subtract tangent squared, that's weird, but it's true. You could factor this as secant plus theta times secant minus theta. Yeah, all sorts of things you can do. Same thing here. The factor is 1 plus sine times 1 minus sine. 1 plus cosine. Yeah. There's lots of different ways you can express it. This one, same thing. You can write it in terms of cotangent squared is cosecant squared minus 1, and cosecant squared minus cotangent squared is equal to 1. Lots and lots and lots of ways you can express these Pythagorean identities. They are so useful and helpful. The main one to remember is sine squared theta plus cosine squared theta is equal to 1. No matter what the theta is, that's always true. Okay. So note that sine squared theta represents, this is just nomenclature, the sine of theta squared. Don't put sine of theta squared without parentheses. That would indicate you're squaring this before you take the sine of it. So either put it in parentheses, that's why it's a lot easier to just write it here. It's the sine that you're squaring of the angle theta. Cosine squared represents cosine of theta squared. It's just easier to write this than having to do the parentheses and so on. Okay. That leads us to example 5, just below there, and it says, let theta be an acute angle such that the sine of theta is 0.6. Find the values of cosine theta. Now, there's several ways you can do this. I know which way they want you to do it now. If you know this, and you're looking for this, you need to find an identity that relates sines and cosines. Well, your reciprocal identities don't. They relate sines and cosecants and cosines and secants. That's out. Your ratio or quotient identities relate sines and cosines to tangents, but not necessarily to each other. So you have to use your Pythagorean identity. And what we know here from the Pythagorean identity, anyone tell me? Sine squared theta plus cosine squared theta is equal to what? Always 1. Well, we know what sine is. Sine is 0.6. When you square 0.6, you have 0.36 plus cosine squared theta. That's equal to 1. You know it is. Let's subtract 0.36 from both sides. So you can make this a 0.00 if you wanted to make the subtraction easier. This adds or subtracts to 0. So you have cosine squared theta is equal to 1 minus 0.36 is 0.64. Now, they said theta was an acute angle, meaning it's in the first quadrant, meaning it's positive. So now when you take a square root, you don't have to worry about plus or minus, you just do the positive square root. And that's what we do. We take the square root of this side, it's cosine theta, and the square root of this side, the positive square root, 0.64. I don't know if you know what that is, but it's 0.8. Alright. Now, I said that's how they wanted you to do the problem. I'll show you how I like to do it. We'll get to that in a minute. Let's first do the B part. What is tangent theta? Well, now that you know sine theta and you know cosine theta, you know tangent theta from your quotient identity or your ratio identity, because you know that tangent theta is equal to sine theta over cosine theta, your ratio or quotient identity. And since you know that sine is 0.6 and we just determined that cosine is 0.8, I really don't like dividing decimals, but your calculator will do it no problem. I like to multiply this by 10 and that by 10 and make it 6 over 8, and then reduce both of those by 2. That would be 3 over 4. So that would be, writing that in a decimal form, is 0.75. There is what your tangent is. Now, that's how they wanted you to do this, using the identities they just gave you. But frankly, in my mind, the easiest way to do this is write you a little thing. Let's just say that this is the same as 3 over 5. Wouldn't you agree with that? 6/10 is 3/5. Okay? Everybody in agreement? Now, as soon as I see that, then I want to draw me a circle. Now, this is a unit circle. No, it's not. Oops, this is not going to be a very pretty circle. I want this to be a 5 circle. Okay? So if that's 5, this would be 2, 3, 4, and 1. This would be 3, 2, 4, and 1. This would be 3, 2, 1, and 4. This would be 2, 3, 1, and 4. Okay. Sorry, this is ugly, but you get the general idea. So the sine is 3 over 5. That's why I made the hypotenuse 5. This is 5, 0. This is 0, 5. You got the general idea. Okay? So it's a 5 circle, not a unit circle. Now, the opposite side is 3. So that's the y value is 3. 1, 2, 3. So that's going to be right about here. Get out of there. Right about there, somewhere there. I may be a little high. Okay? So this is the angle theta we're talking about. Okay? 3 is the height here. 5 is the hypotenuse. And guess what the adjacent side is? Somebody had this last time. 3, 4, see, mine almost came out right on the money here. 3, 4, 5 triangle. And from this, you can see the cosine. This is your angle theta. Sine of theta is 3/5, the cosine of theta is 4/5, and 4/5 is 0.8. And the tangent is 3/4, exactly what we got there, which is 0.75. To me, that's a little easier than doing the Pythagorean identity. However, since they just showed you that one, they wanted you to have the experience of doing it. So let's see how they did it. To find the value of cosine, use the Pythagorean identity. Sine squared theta plus cosine theta is equal to 1, exactly like we did. Okay? And we have that 0.6 squared, that was your sine squared, plus cosine squared is equal to 1, just like we did there. It's hard to read now, but it's there. And so cosine squared is 1 minus 0.6 squared. Why they don't go and square that, I'm not sure, but that would be 0.64. That's the subtraction of that. 1 minus 0.36 is 0.64. Then take the positive square root, because they told you it was an acute angle. Acute angles have positive values for all your things, so that would be the square root of 6.64, which is 0.8. And by the way, if you didn't know that, your calculator does, so you could use your calculator. Excuse me just a minute. I'm awfully dry. I'm also hoarse, sorry. All right, and once you know that, then you can go to the B part, since you know tangent is sine over cosine, that's 0.6 over 0.8, and your calculator would tell you, if you just plug those in, it's 0.75. I did it by reducing a fraction. Same thing. Any questions on that? That's example 5. Now, here's they show you the other part. Using definition of a cosine and tangent, the right triangle shows those results. Rather than using 0.6 and 0.8, why don't you do 3/5, 4/5, and 1, which would be, you could make 3, 4, and 5. Just multiply each of those by 1. 3, 4, 5 works to me a lot better than 0.6, 0.8, 1. Okay, but whatever. That works too. All right. That was example 5. Okay. They're skipping examples 6 and 7. So let's us do that on the whiteboard. All right, we go to 11:15, so we have 8 minutes. Let's see if we can at least get example 6 done. All right, to clear the screen. Okay. Let theta be an acute angle such that the tangent of theta is equal to 1/3. By the way, this is not one of our favorite angles. All we know is theta is acute. Is acute angle? No. Is an acute angle. Okay. Which means first quadrant. Everything's going to be positive there. Okay. Now it says find the value of cotangent theta. That is pretty easy. What would that be? Anybody? 3/1 or 3. Perfect. That was so easy. The B part says secant of theta. Now, again, I know what they want you to do. They want you to use the Pythagorean identity. Now, remember, we did solve one like this, and we said secant squared theta minus 1, well, let's see. No, that's equal to 1 plus tangent squared theta. That was the Pythagorean identity. Secant squared theta is 1 plus tangent squared theta. Okay, we know 1's 1 plus tangent squared theta. If tangent theta is 1/3, tangent squared would be 1/9. Now, I'd rather add that as 9/9, which is 1. Everybody agree with that? Plus 1/9, and that's going to be 10/9. And that's secant squared. Take the square root of that, and you have secant theta is equal to the square root of 10 over 3. The positive. Always positive because it's an acute angle. Now that is an ugly E there. I can't, there. Secant theta is still pretty ugly, but okay. There it is. Done. Secant theta would be the square root of 10 over 3. And if you look in your book, that's exactly what we get. That cotangent of theta was equal to 3, secant theta, square root of 10 over 3. Now, the other way I would have done this is draw me a circle. Okay? I don't draw circles well, but I kind of like using them for clues and hints. Okay, now we know that this is opposite, taking oats away. So 1 squared is 1, plus 3 squared is 9. So this has got to be a 10 circle. Okay, so if that's 10, there's 5. So just imagine that you put in 10 marks here. My marks are all showing up, but they're in there. Okay, and the tangent is 1. That's the opposite side is 1, so that's this one, and 3 would be the adjacent side. Something's not panning out too well here. No, okay. Okay, 1, 3. Okay. 1 would be this, 3 would be that. So we're somewhere 1 divided by 3. Oh, this is, I guess it's better to draw it like this. Opposite side 1, adjacent side 3. Okay. And we're dealing with this angle right here. Now that doesn't look like it's the first one. So this would be, that's what the problem is, the square root of 10. So this should, I'm sorry, so that would be 1 and 9. So 9 would be here. So here would be your angle. That's it. I knew something was not looking right. It's going to be, a very acute angle here. 1 is the opposite side, 9 is the adjacent side. Okay? So this is 1, this is 9, and this is 10. That's it. And then looking at that, cotangent would be, well, you know that's just 3 over 1. That was just so easy to do. But then the secant, if that's the case, then the secant is, and these should be square roots, I'm sorry, but this squared plus cosine is adjacent over this, this is this over that, and take the square root of it, and it's the square root of 10 over 3. That one's not as neat to do on a circle as the others are, but it does work. Okay. Now, and that's what they're showing in the book, only they use root 10 as your radical, as your hypotenuse. Okay. There is a checkpoint right after that. Please do the checkpoint. So how are we doing on time? 1 minute. Do we have time for example 7? I kind of doubt it. Okay, so let's stop right there and figure to do start next time with example 7. Okay, bottom of page 281. Let me get my Yahoo marker in place here. And homework exercises would be either any of the odds 5 through 9. They're all at Calc Chat. This is on page 284 and following. Number 5 is at Calc View. Either 11 or 13. They're both at Calc Chat. Any of the odds 15 to 21. They're all at Calc Chat. And then you should be able to do any of the odds 23 to 27. They're all at Calc Chat. 27's at Calc View. Using a calculator, ones like we did just a little earlier, any of the odds 29 to 35, they're all at Calc Chat. And then using the trig identities that we were just doing, that would be 37 through 41, they're all at Calc Chat. 39's at Calc View. Okay, I think the rest of those I think you probably can do any of the odds 43 to 51. They're all at Calc Chat. And I think you can do any of the odds. And if some of these toward the end are giving you problems, wait, we'll go over some more of these in class. But try to do either 59 or 61. They're at Calc Chat. Now, if you can't get those, don't sweat. Hold off on the application problems till after we do lecture on Tuesday. Tuesday. All right. Any questions at all in the end of 4.2? Didn't we do the end of 4.2? No, we didn't. We're just all within 4.3. Where did we start today anyway? Yeah, we were in 4.3 all day. Okay. So any questions on 4.3? All right. I'm going to stop sharing. I'm sick and tired of sharing. If there's no questions, please, folks, have a safe weekend. This virus is still out there. Don't go into complacency here. Please be safe. Okay. So any thoughts before I close up? Yeah, I'll stop the recording. Thanks for reminding me. In fact, let me stop it right now.